Since everything in the universe is either matter or energy, it makes this the logical starting point for any conversations in chemistry. In general terms, think of matter as the stuff that everything is made up of, atoms, molecules, and other particles, and energy is more an ability to cause that stuff to undergo changes. In modern theories of physics, matter and energy are actually very closely related, kind of thought of as two different sides to the same coin. But in our basic understanding of chemistry, we classify them as two very distinct and different things. And we first focus on matter. Matter being anything that has mass and takes up space. So that gives us another definition that we need to worry about, which is that of mass. Mass is the quantity or amount of matter that something has. Now, if we look at these two definitions, you see a little bit of circular logic because the definition of one is dependent on the other. Basically, the overall definition of matter as being the stuff, the tangible material that things are made up of, and mass is the quantity or measure of that stuff. The law of conservation of matter or mass is one of the most fundamental laws in chemistry, and it says that whatever mass or matter exists, we cannot totally create or destroy any matter. So it's a finite thing that remains constant in the universe. Now, that's with any ordinary or physical chemical processes. There are nuclear reactions, which are actually the most common type of reaction in the universe probably, and matter and energy can be created and destroyed in those processes, but this is not something we see in our basic studies of chemistry. Please get used to using different terminology and definitions. We seldom ever use the term weight in chemistry, and that's because we focus on the term mass. Now, what's different about them? Mass is the true measure of the amount of material in something. Weight is how it's affected by gravity. So as gravity changes from place to place, even within or on the Earth, it has an effect on the weight. So weight is variable. Mass is a constant anywhere in the universe. Consider this example. An object on the Earth and on the Moon would have the exact same mass. They're made up of the same material. But when you consider location, it weighs significantly less on the Moon than it does on Earth. Now, as for changing our terminology, that means when we're describing things in a lab report, we stay away from the words weight, weighing, and scale and focus instead on mass, massing, and balance. In the next step, we learn to break down matter into a couple basic types of matter. We do this by basically studying their properties that we could see or observe. That would be properties at the macroscopic level, and also studying what's going on at the microscopic or particle level. We can begin our explanation of classification with the idea of states of matter. That's one of the easiest ones to see. And understanding the difference between microscopic and macroscopic with states of matter. On the surface, matter may look continuous. However, when you look at it at the particle level, it's not continuous. So solids, liquids, and gases at the particle level, we could see the effects of the individual pieces and how that influences what we are seeing. We look at four basic states of matter, although there are often considered to be more than that. But we focus on the basic physical states of matter, solid, liquid, and gas, and we also take a look at plasmas. A solid at the particle level is made up of particles that are moving slowly, have little energy, and have strong attractive forces. Since they have little energy, they're moving slowly, vibrating in position. These have the least amount of energy. Now imagine adding heat energy to a solid. What happens is as you add heat energy to it, the particles move quicker and quicker. Eventually, the forces of attraction locking them into place are kind of overcome by the movement and speed of the particles, and we get a liquid. In a liquid state, these particles still have strong enough forces to keep them held together, but at this point, the particles can move around freely past one another, and that's why in a liquid, they have a finite size or volume to them, but the shape of them changes continuously. Continue adding heat energy to these, the particles move faster and faster until they completely overcome the forces of attraction that hold them together, and we get a gas state. Of the three ordinary physical states of matter, the gases have the highest energy. They don't have a finite shape and they don't have a finite size. The particles are moving so fast that any attractions there are negligible. They can't hold them together. So the particles move, bounce off each other, and end up as far away as possible. If we continue to add heat energy to a liquid, we get the plasma state. Basically, in a plasma state, the energy that is making the particles move faster no longer can be added to it. You can no longer get the particles to move faster, and instead the energy is absorbed into the atoms, affecting their electrons. A plasma is considered a superheated gas, but it's a little more than that. It's chemically different than a gas because the atoms that make it up ionize. They lose some or all of their electrons because the energy going into them causes the electrons to become excited and actually break free from the atoms themselves. Now, we can use states of matter as well as other physical and chemical properties to classify matter. In general, we ask one question to decide what type of matter we're looking at. Can it be physically separated? The simplest, most basic types of matter cannot be physically separated into anything else, so we consider those to be pure substances. The ones that can be separated are much more complex and made up of several other types of matter. These would be considered mixtures. Now, the term physically separated means, can you separate it without altering the chemical identity of things? In other words, processes like filtering the substance, melting it, using gas chromatography to separate it, or a variety of other physical processes. If it can be physically separated, we're looking at a mixture. And mixtures can be broken into two types too, based on, is it uniform? In other words, is it even throughout? If the answer is no, it's a heterogeneous mixture. But if the answer is yes, it is uniform throughout, you're looking at a homogeneous mixture. On the other side, the simpler substances are pure substances. We can ask a question, can it be chemically separated? And this tells us which of the two types of pure substances it is. If it can be chemically separated into other things, it is a compound. But if you cannot chemically separate it into different materials, then it must be a single element. So back to mixtures. A mixture is a combination of things that is not combined at a set ratio. In other words, you could adjust the amounts in a mixture and you still have the same basic mixture, but the parts of it will be in different amounts. They keep their own properties, so when you put them together, all of the properties sort of are still visible or there in the new substance, but if you separate them, you still see the identity and properties of each item. A heterogeneous mixture, again, are the ones that are non-evenly mixed, where the homogeneous ones are uniform or evenly mixed. So looking at some examples of each of these, heterogeneous mixtures, which are the ones that are unevenly mixed, are things like concrete, which would be made up of sand, water, cement, and gravel. Things like milk are unevenly mixed, fresh squeezed lemonade, which would separate because of the pulp. Stones like granite or marble. River water would be considered unevenly mixed and contain particles of like mud and silt and other debris. They could separate out, but are unevenly mixed. Fog is an example of a heterogeneous mixture, as is air pollution, the airborne particulates that are in air. Now, homogeneous mixtures, which are also called solutions, involve things like sports drinks, Gatorade, Powerade, salt water. These are all evenly mixed. Now, solutions are homogeneous mixtures, so yes, you could still adjust the amounts of each substance, but within any sample, they'll have the same makeup. For example, air, which is a mixture of nitrogen, oxygen, carbon dioxide, argon. Those are the basic components in air. Every sample of air is evenly mixed. Now, if you look at the entire atmosphere of Earth, I understand that the air does vary from place to place, or based on elevation, it could vary a little bit, but within any sample of our atmosphere, it's going to be evenly mixed. Seawater is a mixture, yes, of salt and water, but there's also gases mixed in with it. Any sample of seawater is going to be very consistent with the amount of oxygen, the amount of carbon dioxide, and the amount of water and salt, mixed throughout that sample. If you're looking at the entire ocean, it's a different story. The amounts of those gases may vary from point to point in the ocean as a whole, but with any sample, it's going to be constant. Another good example of homogeneous mixtures are alloys. Alloys are mixtures of metals. For example, brass and bronze, which are both copper mixtures, 14 karat gold, sterling silver, and steel and stainless steel, all homogeneous mixtures. Now remember, a mixture can be separated into its more basic components, not necessarily easily, but it can be separated. So air could be separated into the different elements that make it up. Seawater can also be separated, and brass can be separated. Yes, it'd be more difficult if you have to melt the metal to get it broken down, but nevertheless it can be. All right, on the other side of that chart, we have the pure substances. Pure substances are exactly the same throughout, regardless of where you get that sample from. And if there are different components, they're always there in the same ratio. The element consists of just one type of atom. The compounds consist of two or more elements, but the key is they're chemically joined. That's why the ratio of them has to remain the same. Okay. From there, let's look at some of the properties that we use to classify these materials. Basically, all properties come down to either physical properties or chemical properties. The physical properties are the ones that you can study without altering what it's made up of. Funny thing with chemical properties is you can't study them without actually changing the substance so that it's no longer the same substance. Now, physical properties are broken down into two types. The two types are intensive and extensive physical properties. An extensive physical property depends on how much of it you have. So if you're describing the mass of something, the size of something, or even the weight of something, you're basing it on how much material there is. The intensive physical properties are based only on what it is. So it's not based on a particular sample, like two different samples of copper would have different extensive physical properties, but two different samples of copper, even if one's large and one's small, they have the same basic intensive physical properties. Other intensive physical properties include things like ductility and malleability, which are properties of metals. Malleability is our ability to hammer or roll metals into thin sheets, and ductility is our ability to stretch or draw metals into wire. Color, again, not dependent on how much material you have, only what it is. Crystalline shape, the basic arrangement of the particles that make it up. And the refractive index, which is how light passes through certain objects. All of these depend only on what it is, not how much of it you have. Now, any of the physical properties can undergo changes. They alter how the substance looks and acts, but not what it is or what it's made up of. That's a physical change. The most important physical change is a change of state. For example, if an ice cube melts to water, it still is the same substance at the molecular level. It still has the same basic properties, but it has a different appearance. And of course, you could reverse that process. So any change of state, melting, freezing, condensing, vaporizing, sublimation, and deposition are all physical changes. Chemical properties, on the other hand, are the ones that we cannot study without altering the basic chemical composition of something. Things like combustibility or the ability to burn. The only way to know if something burns is to burn it. Problem is, if you burn it, do you still have the same substance? No, you've destroyed it. The ability to oxidize, which is like reactivity with oxygen. Most substances will combine with oxygen, and once it does, you no longer have the same substance. For example, copper turns green or brown, and that's a form of patina on the surface that is copper oxide. It's different than the copper that was there. Silver tarnishes, iron rusts. These are all oxidized forms of those elements. Generally, a chemical property refers to how it's going to undergo a chemical reaction. These chemical properties then are studied based on those reactions. Chemical changes or reactions are any change where one or more substances is altered into different, chemically different substances. In other words, different arrangements of the atoms. Each of those different arrangements is going to give us different properties. There are certain signs to look for with chemical changes, but keep in mind this list is, don't look at one or two of them, look at all of them and identify a few changes. The first sign of a chemical change is the evolution of heat and light. In other words, think fire. As something undergoes burning, it is chemically altered, and both heat and light are given off. Changes in temperature can be a sign of a chemical reaction. Now for these, think of like the boot warmers or glove warmers or heat packs that you get at the drugstore. They have chemicals inside them that will react once you take them out of the packaging, and they produce heat. You also have like the ice packs, the chemical ice packs that get very cold. Now, think about this. We know objects give off heat. Can an object give off cold? The answer is no. There is only heat energy. So if something feels hot, it's because it's giving off heat energy. It's pumping out that heat energy into its environment. If something feels cold, it's not giving off cold. What it's doing is it's removing heat energy from its surroundings to fuel the reaction. So when something feels cold, it's because it's stealing your heat. Production of a gas, think vinegar and baking soda. Think Alka-Seltzer in water. When the compounds react, they create bubbles of gas that weren't there before. Production of a precipitate is a solid that can form when solutions are mixed. This shows the example of the precipitation of lead iodide from lead nitrate and potassium iodide, two clear solutions, and when you pour them together, you see a solid precipitate appears. A production of an odor that was not there before. We're not talking about spraying perfume where the smell was there the whole time you're releasing it. We're talking about like when you're cooking and you have production of a smell. That could be a sign of a chemical change because that smell is a molecule that wasn't there before. Changes in color, like for example, when you're cooking shellfish and the shells change color through oxidation reactions, again, the color change shows us the reaction took place. Now with explosions, in other words, fire that creates intense pressure, you get production of sound. So that could be a sign of a chemical reaction or chemical change taking place. And the last one is the production of light, whether it be glow sticks or chemicals that you mix together that glow. This would be known as chemiluminescence, and it even takes place in some living things like fireflies. That production of light is through a chemical reaction that's called biochemiluminescence. Now remember what I said. You need more than one or two of these things as a sign of a chemical reaction. For example, I mentioned change in temperature and I said, well, if something feels cold, it's drawing in your heat. That one doesn't, just seeing that doesn't necessarily mean chemical reaction because melting ice, which is a physical process, also draws in your heat energy. So we do have to look at more than one of these things. Okay, so we said everything that exists is either matter or energy. We just looked at matter, the different types of matter, how we classify it, and the different types of changes matter could undergo. Remember, energy is what causes change to matter. And it doesn't matter if it's a physical change or a chemical change. Energy in some way is involved. Energy, the ability to cause these changes, basically can be stored, it can be converted, and it can change forms very easily. However, it is conserved. Remember that the law of conservation of energy, like the law of conservation of matter, says that energy itself is not created or destroyed, but it does change form and travel from one system to another. The two different types of energy, potential energy and kinetic energy. In physics, we consider potential energy just simply stored energy like elastic potential energy or gravitational potential energy. However, with kinetic energy, that's energy in motion. Now, what does this mean in chemistry? It's a little more abstract than in physics because we can't really see what's happening. In chemistry, kinetic energy is caused by the motion of the particles themselves. The kinetic energy of every particle of matter is equal to 1/2 the mass of that particle times the square of its speed. But we're not looking at a large system of particles like in physics. We're looking at the individual particles themselves, whether it be an atom or a molecule. So the kinetic energy, which, yes, does lead to heat energy is based on how fast the individual particles are moving. Potential energy in chemistry is about the interaction between positive and negative charges, your protons and electrons at the most basic level. Attractions and repulsions between them lead to potential energy. So what is the role of energy in any change? Well, every single change will either absorb or release energy into its surroundings. Processes that release energy are known as endothermic. Thermo meaning heat, exothermic. Let me say that again. Process that releases energy is exothermic, meaning heat is exiting the system into its surroundings or leaving the system. A process that needs to absorb energy to take place is known as endothermic. In other words, it's absorbing energy into it. Now, I mentioned how these fit into your ice packs and your heat packs. Those are chemical changes, but how does this take place, or how does this go along with physical processes? Think of ice melting. Ice melting is an endothermic process. It needs to absorb heat energy into it. So it takes heat energy from you to fuel that change, to get the particles of the ice to move faster and break free of one another. But that means that freezing water into ice is an exothermic process. In other words, you have to remove the heat energy from the water to slow down the particles and get them to crystallize into solid ice.